Hello everyone. Let's look into the next stage of the physical design flow, which is the routing and DRC stage. So routing by itself means that we need to route 2 points. So it says that, for example, you have this D in one, okay, and you have this input of flip-flop 1. D in 1 has to be connected to flip-flop 1, or basically there should be a physical wire between D in 1 and flip-flop 1 to maintain a physical connectivity between these 2 points. But from an algorithmic point of view, the software identifies D in 1 as your source, okay, the flip-flop 1 input pin as a target, and the algorithm has to find the best possible solution to connect between D in 1 and flip-flop 1. Okay, so that's basically is the routing algorithm. So while we discuss route, it's not just connecting between two endpoints, but to find out the best possible connection between two endpoints, with one point being the source and the other point being the target. Okay, so there are various algorithms being developed over the time, and we are going to look into one such algorithm. Let's try to remove the netlist and the power lines from here, and let's look into one such algorithm which is called as the maze routing, or it's called the Lee's algorithm. So Lee is a very famous person who actually invented this maze routing concept, though it has got some limitations, but he was the first one to start or to come up with algorithms of routing. So when we say routing, it means that we need to connect 2 points. Let's say we have to connect, let's say we'll take an example. If you have to connect these 2 points from point A to point B, so this point A will act as a source, this will act as a target, and you have to find out the best possible path or the shortest possible path to connect A and B with less number of twists and turns. By twist and turns, we mean that there should not be any zigzag, there should be minimal zigzag lines. Most of them should be L-shaped. There should be very few that should be Z-shaped, and there should be very few lines that will be zigzag shaped. So we are looking for the best possible solution to connect between A and 2. There are various methods to connect point A and point 2, but we are looking for the best algorithm. So from an algorithmic point of view, for the software, it is just two endpoints, and the software has to connect these two points. Basically, there are some search algorithms, there are some kinds of algorithms that it has to run in the backend to understand the best possible route between 1 and 2. But from a physical design engineer point of view, it's a route, it's basically a physical wire. And from an algorithmic point of view, it's basically two different points which has to be connected. Okay, the algorithm doesn't care whether it's a flip-flop or it's a buffer or something of that sort, to some extent. But for what does the algorithm cares about is there are 2 points which we need to connect. So let's look into one such algorithm. We'll remove all the remaining things and keep only this one, because this is again needed, as this acts as a blockage for the routing. So for example, there can't be any route that can go like this and over the top of these blocks and go to the right side. That's not allowed. So we have to take care of this blockage as well, this obstruction as well. For the algorithm, this will be acting as an obstruction. So basically the coordinates that it sees for this particular set of boxes, the algorithm understands that it can't put any route through this particular obstruction. Okay, let's look into the algorithm now. So for example, you have this as initially what the algorithm does is it creates a grid. It creates a routing grid at the back end with these two as a points that needs to be routed. So this is called as routing grid, and there are some standard numbers for this, or standard dimensions of this grid. We won't get into details of that, but there are some standard dimensions. Okay, we're trying to explain the concept of the Lee's algorithm. So there is a routing grid that is being built at the back side of your floor plan, and it already has, if you try to look into any of the tools and you try to zoom in of those tools, you will able to see these routing grids. Okay, and then when the algorithm makes this routing grid, it creates 2 points. So one is called as the source, and the other one is called as the target. Now through the help of this routing grid, the algorithm has to find out a best possible way to connect this source with this particular target. So how does it do that? So what it does, the first step that the algorithm does is it tries to label all of the grids that is there around it. So the first grid, the adjacent grid that it sees next to its source, there are 4 adjacent grids to this particular source. One is this one is this one is this one, and one is this one. It tries to label these grids called as 1. Okay, so all the adjacent grids, all the not the diagonals one, but which are vertical and horizontal adjacent to the source grid, they are being labeled as 1. Okay, let's try to let's do it in this way. Let's try to label all the adjacent one as ones. Okay, now let's take each and every checkboxes for 1. Let's say this particular grid of 1. Now this grid will be this will follow the same procedure. It will label all its adjacent grids as the next number, which is 2. So for this one, the adjacent grids are this one, and this one, not the diagonal ones, only the adjacent grids which are horizontal and vertical to it. So so this grid which is adjacent to 1, this grid which is adjacent to 1, and this grid which is adjacent to 1, they will be labeled as the next number. Similarly, let's say we'll take one more. Let's say we'll take this, or let's say we'll take this grid, this particular grid box. Okay, so this has 1, and its adjacent grid boxes are this one, and this one. So they will be labeled as the next integer, which is 2. Similarly for this one, similarly for this one. Let's do it. Okay, so now each and every ones over here are being the adjacent grids for this grid box 1 has been labeled as the next integer, which is 2. Similarly, it has been happened for this one also, it has been happened for this one, and for this one also. Next is we will take this 2, we'll take each grid box which is labeled with 2 and label its adjacent grid with the next integer. So for example, let's say this particular grid box, it is being labeled as 2. The adjacent grid box for this grid box 2 is this one, it's this one, and it's this one. So let's try to label it as the next integer. So we'll try to take this particular grid box, and its adjacent grid box will be labeled as the next integer, which is 3. Similarly, we'll be doing it for all 2s. For example, for this 2, the adjacent grid box is this one and this one. For this 2, the adjacent grid box is this one, and this one. Okay, and not the diagonals one. Diagonals are not the adjacent ones, but they are diagonal. So we are looking for vertical and horizontal adjacent ones. So for example, for this grid box which is labeled as 2, its adjacent grid boxes are this one, and this one, and they will be labeled as the next integer, and the next integer over here is 3. So let's see whether we have done it or not. So we'll put a 3 over here. So now if you see any of the 2s, any of this particular 2, all its next adjacent grid box, for example this one, and this one, are all labeled as the next integer number. For example, now let's say this 2, it has got 2 adjacent, one is this one and one is this one. This is also an adjacent, but it has already been labeled. So we have to find out the next unlabeled adjacent box to get labeled. Okay, so the next adjacent unlabeled box was this one for this 2, and it has been labeled as 3. And this grid box, which is again adjacent to 2, is being now labeled as 3. And you can pick up any of the 2s over here. For example, let's say you pick up this 2 which is pointing over here. The adjacent grid box to it's labeled as 3, and the next adjacent grid box is being labeled as 3. Okay, and the same procedure follows. So we have to take all the grid boxes which are being labeled as 3, for example this 4, this 4, this 4, and this 4, and take the adjacent grid boxes of it and label it as the next following integer. Okay, so for example, this particular grid box which is now labeled as 3, its adjacent grid boxes which are empty are this one, and this one, and all this will be labeled as 4. Okay, so what we'll do is, since we have to connect, we have to do even more resourcing of the, or even more labeling of the grid boxes, and we are already running out of time. Let's try to take this particular algorithm in the next video. Thank you.